Hi everyone, I am Hanumat Shastri. In today's lecture, we are going to discuss about optimization problems and another concept, backtracking. So first of all, we will discuss about optimization problems. So at the outset, we have two types of optimization problems. One is minimization problem and other one is maximization problem. First, we will understand what is optimization problem. In the real world, whatever the problems we see, especially in the field of artificial intelligence, we can convert those problems in terms of optimization problems. So if we see the definition of optimization problem, let us say you will be given a larger search space. You will be given a larger search space. Assume this is the search space and we call it as S. And in this search space, there will be various solutions. Let us say these are all solutions for our problem. Okay. And in this search space, there are some specific solutions which can be known as feasible solutions. And we call it as F. We call it as F. Feasible solutions. What is feasible solution? So if we take the real world problems will be having various solutions. Out of for getting those solutions to solve the problem, we will be having certain constraints. We will be having certain constraints. Feasible solutions are those solutions which satisfies the constraints of the problem. So in larger search space, yes, if we consider yes, we will be having solutions here, and your feasible solutions is a part of solution space. Feasible solutions are nothing but the solutions which satisfies the constraints of the problem. So now in these feasible solutions, we need to find out most optimized one, that means which will give us most benefit to our problem. So what is optimized one? So the optimized one depends upon the problem which we are dealing with. As we discussed earlier, in optimization problem, we have two classes of problems. One is minimization problem, the other one is maximization problem. Let us say, if at all you are finding a solution for a problem where you need to find out the optimized cost. You need to find out optimized cost. In the sense, we want to reduce the cost of the problem. So in that case, we will go for the type of minimization problem. If at all we are dealing with the resource allocation, or if at all we are dealing with certain problems where we want to maximize the profit, in that case we will deal with the maximization problem. Okay, so the minimization problem we can define, let us say in this F feasible solutions, you have various solutions. Out of that, you want to find out a particular X, that means X, most optimized one X, out of the feasible solution. Let us consider all other solutions are all other solutions which are available in F are Y y. So now you have to find out this x. When you compare with all other solutions, it must be minimized. That means evaluation of x less than or equal to evaluation of y. Okay, now this y belongs to f, and when we consider about maximization problem, we need to find out a certain x. When we compare with all other solutions, x must be greater than or equal to that. So at the same time, y belongs to f as well. Okay, so when we talk about minimization problem, the objective function is to minimize, and when we talk about maximization problem, the objective function is to maximize. So here the objective function in minimization problem, we call it as cost function or energy function. Cost function or energy function. And when we talk about maximization problem, the objective function would be utilization function or it can be reward function. It can be reward function. So here the objective function depends upon the problem which we are dealing with. If at all we are dealing with minimization problem, our objective function can be cost function or energy function, or if at all we are dealing with maximization problem, the objective function will be utilization function or reward function. Okay. As we discussed earlier, the optimization problem will be having constraints. In earlier discussion, we classified optimization problem into two categories based on objective function. Based on objective function. Now, we will classify the optimization problem into two more categories based on constraints. Type of constraints. Already we discussed about constraints. So in real world, every problem will be having certain constraints. If at all you want to solve that problem, and if at all you want to get a solution out of the problem, we need to fulfill the constraints of the problem. Without fulfilling the constraints of the problem, even though you get a solution, that solution is incorrect to that problem. So the constraints are nothing but rules and regulations of that particular problem, or we can call it as a conditions which are applicable over that problem to obtain a solution out of that problem. So based on the constraints which are applicable over optimization problem, we can classify the optimization problem into two categories: soft constraint problems, and second one is hard constraint problems. Hard constraint problems. So we are well known about the problems which falls under soft constraint problems and hard constraint problems as well. I will give you an example. This under soft constraint problem, we have already solved in our previous courses, maybe in design and analysis of algorithms and network communication, data communication networks. One of the problem which we solved was network optimization problem. network optimization problem. So this is a classical example for soft constraint problem. When we talk about hard constraint problem, the classical example for hard constraint problem is knapsack problem. We know the network optimization problem as well as knapsack problem also. In network optimization problem, we need to find out the shortest route in the given network with the lowest energy cost. So this is what our network optimization problem. So if we start putting the constraints over the problem, we need to minimize the number of packets lost, and we need to improve the throughput, and etc., which comes under network optimization problem. If we consider a simple network optimization problem, the simple network optimization problem falls under soft constraint optimization. And when we talk about knapsack problem, it is a hard constraint problem. You will be given a bag which is a limited weight, and you will be given a certain amount of articles which has associated weight and associated profit as well. Out of that, you need to get the number of items which will yield you the maximum profit when you compare with all other items which you have not taken. So this is what the knapsack problem. So this comes under hard constraint problem. Okay. So we have solved knapsack problem in our previous courses. So by using two classes of algorithms, we have two types of knapsack problem. One is binary knapsack, other one is fractional knapsack, right? And we have solved knapsack problem, the various classes of knapsack problem, using greedy algorithms and dynamic programming. Both these techniques are helpful to solve the optimization problems. Now we understand what is optimization problem, what is objective function, and what is a constraint, and various classes of optimization problem based on objective function and constraints. Now we will focus on the classes of algorithms which can solve the optimization problem. So there are two classes of algorithms. One is local search and other one is global search. So to solve optimization problem, we have two categories of or two classes of search algorithms. One is local search algorithms, other one is global search algorithms. In local search algorithm, we have example is greedy, so one of the example for local search is greedy algorithm, and global search algorithms will explore brute force algorithm, brute force algorithm. These are example algorithms, example class of algorithms under two classes of search algorithms. Now we are focusing in this lecture on local search algorithms to solve optimization problems. Local search algorithms to solve optimization problems. So What is local search? The solution, let us say, in this entire solution space, already we know solutions are available in the search space, and we need to find out certain x which can satisfy either minimization according to the objective function or maximization according to the objective function, provided that it satisfies the constraints of the problem. Let us assume if you have a larger search space, if at all you are exploring for the solution, most of the times the global search algorithms will take the time complexity exponential, and space complexity also be high. Reason why is it has to explore the entire search space, so that it takes larger amount of time, and to explore the entire search space we need to store certain amount of the solutions for our reference to compare with the previous or the upcoming solutions, so that we need large amount of space as well. In global search algorithms, time complexity and space complexity is high, but the solution is guaranteed that it is always optimized when we compare with all other available solutions in the given search space. But if at all we want to solve a problem in a certain amount of time by utilizing minimized search space, though the optimized solution may not be the global best, it can be somewhere nearer to the global best solution. In that particular scenario, we will go for the local search algorithms. So, most of the cases in optimization problems, we have one more class of algorithm, one more class of problem depends upon the objective function, that is pure optimization problem. Whenever we are using pure optimization problem, whenever we are having pure optimization problem, in that particular case, it is better to use local search algorithms. So, in local search algorithms, it will take time less, space also less when we compare with global search algorithms. Now we are entering into another topic of this today's lecture, that is backtracking. It is backtracking. As we discussed earlier, to solve optimization problems, we need various classes of algorithms. So, one of the algorithm to solve the optimization problem is backtracking type of strategy. So, backtracking type of strategy is helpful when we don't know the solution available space and we don't know the path to reach the solution. In that particular scenario, what we do is we will start exploring the solution in stepwise. At a particular point of time, if we find that this path is not feasible to explore the solution further, we will roll back to the previous state and we start exploring the other path for searching of the solution. This is a kind of global search strategy. This is a kind of global search strategy. as we know that the search strategies are two categories. One is informed search, other one is uninformed search. So under uninformed search, we have BFS, DFS and backtracking as well. Under informed search category, we have A star algorithm, AO star, etc. So backtracking is a variant of depth first search strategy. Backtracking is a variant of depth first search strategy. So which comes under uninformed search strategies. So most of the times when we implementing the backtracking algorithm, we use recursive function to implement the backtrack algorithm. So recursive function is one of the heart of backtracking algorithm. When we consider a recursive function, there will be two cases. One is base case, other one is recursive case. Base case and recursive case. If the solution is found, then base case will take place. If the solution is not found, then it will take the recursive case and it start exploring the search space further, or it will roll back to the previous state and it starts another path until the solution is found. So when we talk about backtracking algorithm, it takes big O of M space. When we compare with all other, or when we compare with other search strategies which comes under uninformed search strategies, so it takes lesser amount of space, that is big O of M. Reason why is the exploring of nodes will reduce the amount of search and it will reduce the amount of memory which is required by the algorithm. We will see why it needs lesser amount of memory. One of the important concept is when to use backtrack algorithm and why to use backtrack algorithm, though we have various uninformed search strategies. So when to use backtrack algorithm, already we discussed. I will elaborate further. If you don't know the solution, you start exploring the tree from a particular node and you will start exploring the tree to the next node, and you find that that particular strategy or that particular path is not feasible to explore the solution, or you might have hit the dead end and you don't get the solution. In that particular case, what you do is you will roll back to the previous states and you will start exploring the another path. So even that particular path is also not giving the solution, then you will take another path. So this is called backtrack algorithm. That means you will take a step further and you will roll back that step to the previous state and you will find out another path in order to find out the solution. That is called backtrack algorithm. You can see in the PPT. So as I explained you, backtrack is useful when you can incrementally build partial solutions and you can sometimes quickly determine that partial solution cannot lead to a complete solution. In that case, you can stop improving the partial solution, backtrack to the previous partial solution and continue the search from there. Let us say, see this animation in the PPT, you can find. So I started exploring the solution and I hit the dead end and I did not find the solution. That's why I have taken back to the previous state, and I have chosen another path in order to explore my solution, and in that particular path also I did not find solution. That's why I have taken back. I have taken back to the root node. Then I have taken completely new path and I further proceeded. There also I did not get solution. Then I have taken back and I explore the tree in this way. Finally, I get the solution. So here, if you see in the PPT, I started at a particular let us say I have a solution here. I don't know that my solution is existing here, and I started exploring from this point. I have various nodes. I have various nodes in my search space, and I started exploring my search space from this point onwards, and I don't know where my solution is existing, and I don't have any clue about the probability of my solution lies in the search graph. So that I need to explore the entire search space by applying the backtrack algorithm. So now I started exploring from this point. I have initially chosen this node and this is not a solution. So there are further paths are available in this solution space, so that I have taken this path and I did not find, this is the dead end, and I did not find my solution. That's why I have taken back. This intermediate state has another path. I thought it can be a solution, but it is also a dead end. So that's why I have taken back. So now this particular node I have explored completely. Then I am taking back. In the same manner, I will explore this node as well, and I don't find the solution. I will take backtrack. So I will explore this node and I will explore further this node, then I find the solution. Here, this is a variant of depth first search. The reason is exploring of nodes or expanding of nodes will be in the passion of depth first search strategy. At the same time, I discussed earlier, it takes lesser amount of space. Reason why is, while I am exploring this node, I explore this node, I explore this node, and I explore this node. Once I did not find this is not the solution, then I remove this, I will come back, I will explore this, and when I come back to the previous state, that is root node, I will completely this entire thing from my memory space. So that means whatever the successor nodes are coming up, those nodes will only be kept in the memory. That's why it takes lesser amount of space when we compare with other search strategies which comes under uninformed search strategy classification. So backtrack can be implemented in various cases, and to understand the backtrack algorithm, easily, we have sample algorithm, sample problems and well-known problems. Those are solving maze, graph coloring problem and N-Queen's problem. So in solving maze, first of all, we will start beginning the maze. If at exists the return true, that means it's a base condition. As we know that backtrack algorithm employs the recursive function. So if at all we are employing a recursive function, there will be a base case and recursive case. So the base case would be, if you find the solution, return true, and otherwise explore the recursive function, start employing the recursive function. In recursive function, recursively find the path as we discussed in the previous example, and return with the first successful step, return false if all steps fail. So in this fashion the solution will be found. And another classical example for backtrack algorithm is N-Queen's problem. N-Queen's problem. N-Queen's problem is nothing but you will be given a chessboard with n by n dimensions and you will be given n number of queens, and you need to place those queens on that particular chessboard in a fashion that those queens should not attack each other. This is the constraint. Already we know that if at all we are solving a optimization problem, the optimization problem will be having a objective function and will be having a constraints as well. The objective function is to place the queens on the chessboard, the n queens on the chessboard, and the constraint is those queens should be placed in a manner where each queen should not attack any other queen in the given chessboard. So here 2 by 2 chessboard, placing queens on 2 by 2 chessboard is not possible, impossible, and the problem starts from 4 by 4 chessboard, and the classical from 4 by 4 you can have any class of chessboard, any number of chessboard which will be in the dimension of n by n, and you will be given n number of queens, so that you have to place on the chessboard without attacking. The queens should be placed without attacking each other. So we will see the classical n queens problem by using 4 by 4 chessboard, on 4 by 4 chessboard. Just assume this is the chessboard, and with four by 4, and you have given 4 queens. Let us assume Q1, Q2, Q3, Q4, and you need to place all these 4 queens on this chessboard without attacking each other. We know that queen moves diagonally, horizontally, except in L shape. Any queen moves in all directions. Okay, so now we don't know how to put these queens on this chessboard without attacking each other. Now initially I keep my Q1 on this particular cell, that so that I cannot place any queen on this row. The entire row is seized. If I place any other queen on this row, then q1 attacks with some other queen which I placed on this particular row, so that this entire row is seized and this entire diagonal is also seized and this column is also seized. Now this is not the solution and this is not the solution, this is not the solution, this is not, 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 this is not. Now I have option to find the next queen which is in the row, that is q2 here, right? Now this is not the solution, this is not the solution, this cannot be a solution, and I have option to place q3 here or here. I assume I place the q3 here, right? Now what happens? I placed 3 queens on the chessboard and one more queen is left over. I cannot place this q4 on this chessboard. The reason why is this is not the path of exploring the solution. So that what I need to do is I need to take backtrack and I need to replace this q3 somewhere. To replace q3 I need to replace q2 somewhere, and to place q2 I need to replace q1 somewhere. That means I have reached to the root node to replace the given queens in a different fashion, so that I can have the solution. Now the solution, I will place q1 here, so that I can place q2 here, and I can place q3 here, and I can place q4 here. This is the solution for 4 by 4 queens problem. So see in the PPT, here we are not exploring at a particular point of time all possibilities. We are exploring one way of possibility to obtain the solution. That's why we are keeping those possibilities only in the current memory, so that it takes lesser amount of space. Backtracking prunes entire subtrees if their root node is not viable solution. The algorithm backtrack up to the tree to search for other possible solutions. So on the screen you can find 8 queens problem. And the solution is given on the PPT. You can see on the first row I have placed, and 2 7 I placed another queen, and 3 5 I placed another queen, and 8 4 8 2 2 and 4 and 6 4 and 7 6 and 8 3. This is the arrangement of queens for 8 by 8 chessboard. To explore this solution, we have to employ the backtrack algorithm. So as we discussed earlier, since backtrack algorithm employs the recursive function, every recursive function will be having 2 cases. One is base case, other one is recursive case. Base case will happen when you finish the problem, and recursive case will take place when you are exploring for the solution. So the base case and recursive cases are available on the screen. You can see if there are no more columns to consider, you are finished. And recursive step is if you successfully place a queen in the current column, consider the next column. If you cannot place a queen in the current column, you need to backtrack. So this recursive step will take place until you find the solution. Now we discussed about backtracking algorithm. Backtracking algorithm is one of uninformed search strategy which follows the depth first search strategies, which takes a big O of M space, and it explores the entire search space in order to find out the solution. Now we will recap whatever we discussed in today's lecture. Initially we started discussion on optimization problems. In optimization problem, we know there will be objective function and there will be certain constraints. We need to find out the solution. That means we need to obtain the solution depends upon the objective function by satisfying the constraints of the problem. Based on objective function, we can classify the optimization problem into two classes. One is minimization, other one is maximization. And based on the constraints of the problem, we have two classes: soft constraint problems and hard constraint problems. To solve the optimization problem, we have two classes of algorithms. One is local search algorithms, other one is global search algorithms. And we entered into the concept of backtracking. Backtracking is a search type of algorithm which comes under uninformed search strategy. It is a variant of depth first search strategy. So we start building the solution at a particular point of time. If we find that intermediate solution at a particular point of time, the progression of the solution will not lead to the actual solution, then we stop exploring the tree further and we backtrack to the previous state and we choose another path in order to find out the solution. Even that path is also not suitable for exploring the solution, we will backtrack and we will explore another path until we find the solution. So it is a recursive class of algorithm. So it takes big O of M memory. So this is what we have discussed in today's lecture. Thank you. Have a nice day.